Say we have a system, and we want to learn more about it through observation of its behavior. Experimental Hamiltonian learning may provide a way of doing so by measuring and simulating it. For that, we use the Bayes rule, which allows us to characterize a probabilistic phenomenon by sampling from it. By characterize, we mean finding the values of some hidden variables that we know govern the outcomes. Since quantum measurements are, as stated by the Born rule, probabilistic phenomena, this can be used to infer the parameters of quantum systems using data from experiments. This can be as conceptually simple as finding a frequency. We start with a parameterized description of our system. Here the shape represents a model Hamiltonian, and the color represents the parameter. Note that the color is an unknown. However, we should be able to perform some measurements whose results it affects, and thereby gain some insight on it. We must also be able to simulate our system for a range of possible parameters. That way, we can tell how likely the behavior induced by them would be to match the actual systems, if we were to perform the very same measurement operations. We start with some guess on where the real parameter could be. Here the lack of color represents a lack of previous knowledge, which would amount to using a flat prior distribution over all of the possible region in parameter space. So now we can perform an experiment and obtain a datum. Then we do that again, and again, and again. Well, that's enough squares. Now we put together all of this data and we will have an improved guess of what our mystery color is. We can even leverage this freshly acquired knowledge to design our experiments so that they are as informative as possible. That is, we use our results to inform our next choice of experiment control. The key idea is that, apart from the choice of a starting point, we'll be sampling from the likelihood of each of our possible parameters having generated the vector of data we actually registered. Hopefully, this will peak around the real value. So far, we have talked about Hamiltonians and single parameters, but this procedure can also be applied to open quantum systems and to multiple parameter cases. That will require dealing with better suited descriptions for those systems, like master equations and more complex distributions, with increased dimensionality and likely multimodal due to redundancies in the dynamics. We must use suitable sampling methods, such as Hamiltonian sequential Monte Carlo, to efficiently explore the parameter space. These adaptations should help learn the physics of more realistic quantum systems.